Welcome to Math Explorer Infinity, where we break mathematics into pieces to make it more understandable. So today we get to explore Hilbert sums and Hilbert bases, two incredible mathematical tools that can simplify complex concepts in a way that every mathematician or every math student can relate to. Imagine you are a student preparing for a challenging math exam. Say you are preparing for a functional analysis exam, and you have a collection of textbooks to study from. Each textbook covers different topics, right? And you need to understand the material thoroughly, right? I mean, you definitely don't want to fail your exam. You can think of Hilbert sums like your ability to study from multiple textbooks at once. So just as you want to extract um, valuable information from each textbook without mixing them up, Hilbert sums allow you to mathematically combine different mathematical textbooks while preserving their unique content. I mean, it's like having a magical notebook that helps you organize and absorb knowledge from various sources, making your study therefore more efficient. Now, consider Hilbert bases as the essential tools in your study kit, right? Like a set of, I would say, reliable highlighters. Each highlighter allows you to emphasize specific key points in your textbooks. Hilbert bases are like the crucial tools in mathematics, right? I mean, a set of vectors that help you focus on essential concepts and highlight important ideas. So just as a good set of highlighters makes studying more effective, Hilbert bases make it possible to represent and understand complex mathematical concepts with clarity and helping you therefore to ace your mathematical exam. So as you navigate your mathematical journey, think of, I strongly invite you to think of Math Explorer Infinity, this channel, as your super study tool that brings you I would say, the magic of mathematics in an engaging and educational way. So just like Hilbert sums and and Hilbert basis, right, enhance your learning experience. Subscribing to Math Explorer Infinity is like gaining access to a hidden treasure trove of mathematical knowledge. So don't miss out this resource, right? Click the subscribe button now. Yes, now, I said now. And let's explore this the fascinating world of mathematics together. So we start our exploration with a definition. So definition. So let En, right, be a sequence of closed subspaces of closed oops, subspaces of the Hilbert space H. Right. So let me just highlight close. So one says that H is the um, the Hilbert sum of the ends, right? And you write H equals, you have this, I'll just put it this way, oops, you write H to be like, the direct sum of the ends if the first property is that the spaces, let me put it in color, so the spaces En are mutually orthogonal, right? So this means maybe I use this color rather. So this means the scalar product of u and v, is equal to 0 for every u in En and for every v in Em, right? Provided that n is different from m. And the second property to be fulfilled is that the span, this is just my notation. So the span, this is the span of the union of the Ens, right, is dense in H, right? I mean, in the linear algebra sense, right? I mean, finite linear combinations of elements belonging to the spaces En. So if A and B holds, then we say that H is a Hilbert sum of the Ens. Okay, so now let's state our first theorem. So this is theorem 5.9. Okay, so assume that H is the Hilbert sum of the Ens, right? So we just highlight Hilbert sum. Now, given a point u, right, in H, given u in H, right, put it in color probably. Define un to be the projection of u onto En, and Sn is nothing else than the summation over k moving from 1 to n of uk. So define un and Sn as follow, right? Then we have, we call it 19, the first relation. The limit of Sn, right, is equal to u, right, as n goes to plus infinity, and the summation of the norm of uk squared, right, k running from 1 to infinity is equal to the norm of u squared, right? I mean, and this is, I mean, this relation here is known under the, I mean, this is the Bessel-Parseval identity. Okay, so while it is actually usually convenient to use the following lemma, which is actually kind of a simpler version of this, I mean, of the previous theorem. So let's have this lemma first, then we will come back to the proof. It looks ugly, sorry. So lemma 5.1, good. Now, assume that Vn is any sequence in H, I mean the Hilbert space H, right? Such that this is relation 21, such that the scalar product, I mean, such that the Vn are pairwise orthogonal. So the scalar product of Vn comma Vn is equal to 0, provided that m is different from n, right? And also relation 22 holds. This is the series is absolutely convergent. Okay, moving from 1 to infinity, this is finite. So under condition 21 and 22, right, if you put let's call it Sn again to be the summation of the vk running from 1 to n, then the limit, I mean, we can conclude that the limit that we call S, right, of Sn, as n goes to plus infinity exists, right? And moreover, call it 23, I mean, relation 23 also holds. And this is the norm of S squared is equal to summation of the norm of the vk squared, k running from 1 to infinity. Okay, so the proof of this lemma is relatively simple, right? Because to prove the existence of, I mean, of the limit, right, to prove that Sn converges to a point S, right, we will basically show that Sn is a Cauchy sequence, right? And then we use property 21 to show that 23 actually holds. So this is basically the main idea of the proof. So proof of lemma 5.1. Okay. Well, now observe that for m strictly greater than n, right? Let me put it here. We have the norm of Sm minus Sn. As I said, we want to show that Sn is a Cauchy sequence. The norm of Sm minus Sn squared, right, is equal to, let me go slowly, this will be the summation of the vk, k running from 1 to m, minus the summation of vk, k running from 1 to n squared. But this is exactly, because m is strictly greater than n, so this is the summation over k moving from n plus 1 to m, right, of summation of vk norm squared, right? And this is equal to the summation over k running from n plus 1 to m, right, of the norm of vk squared, right? Well, you may wonder how we get this equality, but this actually follows from the fact that the Vn's are pairwise orthogonal. So Vk, scalar product of Vk and Vj is actually equal to 0, provided that k is different from j, right? And now, what you should see, or you should notice, is that let me use this color, probably this one. So observe that this actually goes to 0, right, as n goes to plus infinity, right, because this is actually the tail of converging. Remember that from analysis 1 or 2, that the tail of convergent series, right, tends to 0, right? So because remember we had the assumption that the summation of the norm of Vk squared k running from 1 to infinity, that this is finite. Okay, so it follows that Sn, right, is, you can put an n here if you want, is a Cauchy sequence, right? And thus, because H is a Hilbert space, thus complete, and thus we write it here. Let's be defined to be the limit of Sn exists, right? Now, on the other hand, we have we have that the norm of Sn squared is equal to the summation of the norm of Vk squared, right? K running from 1 to n. Right? This equality again follows from the fact that the Vn's are pairwise orthogonal, right? So from this relation, to take the limit as n goes to plus infinity, right, we obtain 23, right? We obtain relation 23, which was actually saying that the limit of the norm of Sn squared, right, which is exactly, the norm is continuous, so you can put the limit inside. This is exactly the norm of S squared, so this is therefore equal to the summation of the norm of Vk squared k running from 1 to infinity. So with this, we end the proof of lemma 5.1, and now we can actually go into the proof of theorem 5.9. Okay, proof of theorem 5.9. Okay, now since un, right, remember we define un to be the projection onto en of u, right, since this equal to this, since un is the projection of u onto en, right, we have by, we call it 8 back then. You can check out, this was actually we have by the characterization of projection onto a closed subspace. Right, I mean, this was actually, I strongly invite you to check out my video was actually on Hilbert spaces, I think so. Hilbert spaces elementary properties. I will put the link to the video at the upper right corner of the screen. So we have by characterization of the projection onto a closed subspace, the relation 24, right? We have that scalar product of u minus un comma v, right, is equal to 0, right, for every v in En, right? And in particular, I mean, they say in particular, you should take v to be un, right, in relation 24. We get that the scalar product of u comma un, right, is equal to the norm of un squared, right? And this hold for every n, for every n, right? Now, this means, you should take the summation, so this means that the scalar product of u comma sn, right, you should take the, let me go probably slowly, so as not to get you confused. So this means the summation of the scalar product of u and uk, right, k running from 1 to n, right, is equal to summation of the norm of uk squared k running from 1 to n. Right, now if you use the linearity of the scalar product, so this means that the scalar product of u comma sn, right, is equal to the summation k moving from 1 to n, right? But we also have call it relation 25. We also have that the summation of the norm of uk squared, right, is equal to the norm of sn squared, right, k running from 1 to n, right? This follows from the fact that remember, Sn is the summation of the uk k running from 1 to n, right, and the ends they are mutually orthogonal. Okay, so we also have 25. So and thus we obtain that scalar product of u and Sn, right, is equal to the norm of Sn squared, right? If you plug, you replace this here, right? So you have that the scalar product of u and Sn is equal to the norm of Sn squared, right? And then by Cauchy-Schwarz inequality, you know that this is actually less or equal than the norm of u times the norm of Sn, right? So by simplification, it follows that the norm of Sn, right, is actually less or equal than the norm of u, right? I mean, if you square everything, you get that, and therefore summation of the norm of uk squared, right? So let me just check something. Yep, summation of the norm of uk squared. I was actually kind of confused whether I use v or u, but I think everything's okay. So therefore we have that this summation is less or equal than the norm of u squared. Okay, so this means if you take the limit to make n goes to infinity, you get that the norm of uk squared k greater or equal than 1, right? It's actually less. So let me just write k moving from 1 to infinity. It's also equal than the norm of u squared, which is actually finite, right? But before we proceed, let me just draw your attention on something. So this relation here is known under, this is Bessel-Parseval inequality, right? So therefore, since this hold, right, we may actually apply, because the un are actually pairwise orthogonal, we may apply, lemma 5.1 that we just proved, right, and conclude that the limit of Sn exists, right? Now, our goal is now to identify S, right? So now, let's identify S, right? Without even the assumption that, without the assumption that the span of the UNs, right, is dense in H. Okay, so for that, just to avoid carrying span of the union, so let F be the linear space spanned by the ends, right? So we set F to be the span of the union of the ends. Okay, so our claim is that, oops. So we claim that the limit S is exactly the projection onto the closure of F, right, of U. And then we call this relation 26. So how does this hold? Indeed, we have that the scalar product of U minus Sn comma V, right, is actually equal to 0, right, for every V in EM, right, provided that M is actually less or equal than N. Well, how do we see that? You just need to, just hide U minus, let me just write it down here. Just write U minus Sn as U minus, I would say, Um, right, minus the summation of UK, right, over K different from M, right, to n. Okay, so now this means that this scalar product of u minus Sn comma v, right? So this will be equal to the scalar product of u minus um comma v, right, for every v in em, right? Why? Because the ens are actually they are mutually orthogonal, right? So the scalar product of u minus Sn, and I mean, what I want to say is that, let me just take this. What I want to say is that the scalar product of, of this part, yes, of this part here, probably I write it. I want to say that the scalar product of this and v, right, this is exactly 0, right? Because v is actually in em, right, and this quantity here, all of them will live in different spaces, except, in different spaces. In spaces that are actually different from em. And because the em are actually, the ens are actually mutually orthogonal, the scalar product will be 0. So this scalar product is equal to this, but this is actually 0, right? Because this is again the characterization, because it is 0 because u, probably not u, yes, um, I think it's actually the projection onto, yes, by definition, it's actually the projection of u onto em. So by definition, this will be 0. Okay, so we all agree that this scalar product here of u minus Sn comma v is equal to 0 for every v in em, provided that m is actually less or equal than n. Now, as n goes to plus infinity, right, we obtain that the scalar product of u minus s comma v is actually equal to 0 for every v in em, right, and for every m, of course. So, and thus the scalar product of u minus s comma v is actually equal to 0 for every v, for every v in f, right, because f is actually the, it's actually the linear space spanned by the ends. So this implies, which implies that this minus this comma v is also equal to 0 for every v in the closure of f, right? Now, on the other hand, Sn, an element of f, right? For on the other hand, Sn belong to f, right? For every n, right? And at the limit, we get that S, right, which is the limit of Sn, is an element of the closure of f, right? So this means that we can, from this relation here and from this, right, we can say that S is the projection onto the closure of f of u, right? So this was actually our claim, so we prove it. Now, if the closure of f, right, is h, right, then we get that S is actually equals to the projection of U onto the closure of F, which will be the projection of U onto H, but this is exactly U, right? So passing to the limit as n goes to plus infinity in relation 25. Let me just recall what relation 25 was. So this was actually the summation of the norm of uk squared k moving from 1 to n. This is equal to the norm of Sn squared. So passing to the limit in this relation, we get the Parseval's identity, or the Bessel-Parseval identity that we denoted by 20. So this was the summation of the norm of uk squared k running from 1 to infinity is exactly the norm of S squared, which is the norm of U squared. So with this, this is the end of the proof, right? So okay, so now let's have another definition. Let me just, as a matter of style, let me just drag it a bit down. Good. Okay, so a sequence. Now we want to define what a Hilbert basis is. A sequence, say En, right, in H, the Hilbert space H, right, is said to be an orthogonal basis. Right, of H, or Hilbert basis, right, if the sequence En satisfies the following properties. Right, so the first one would be, number one, the norm of En is equal to 1, right, for every n, and the Ens are pairwise orthogonal, so scalar product is 0, provided that M is different from n, right, and you also need the linear space spanned by the Ens to be dense in H. So the linear space spanned by the Ens, right, is dense in H. Right, so this means that the span of, put it like this, right, of the union of this n running from 1 to infinity, so the closure of this is exactly H. Okay, so if 1 and 2 are fulfilled, then we say that En is an orthonormal basis. Oops, I wrote orthogonal instead of orthonormal, because the orthonormality actually occurs here, right? The norm is equals to 1, so sorry for that. An orthonormal basis. Orthonormal basis. Okay, good. So let's have a look at the corollary, right? Corollary 5.10. So let En be an orthonormal basis. So we have an orthonormal basis, then every element U in H, right, can be represented. I mean, for every element U will be then for let me squeeze it here. Then for every element U in H, right, we have that U is the summation, right, of the scalar product of U and Ek, right, times Ek, K running from 1 to infinity, right? So this is also another way of saying that U is the limit as n goes to infinity of the scalar product times Ek, K running from 1 to n. Okay, so you have this, and you have again the, Parseval identity, right? And this is exactly the consequence of theorem 4.9, summation of up to the value of U, comma Ek squared, K running from 1 to plus infinity. Okay, so let's go into the proof. Okay, so let U in H be given, right? So it is given. So now, since En is an orthonormal basis, an orthonormal basis of H, right? H is a Hilbert sum. H is a Hilbert sum of the spaces En that we define to be the span of En, right? For this is for every n greater or equal than 1. Now, moreover, the projection of U onto En, right, is equal to the scalar product, right, times En, right? So using theorem 5.9, this was the first theorem of this lecture. So using theorem 5.9 and lemma 5.1, right, we get that U is the summation of a projection onto En of U, right, n running from 1 to infinity, right? But this is exactly summation of U, or the scalar product of U and En times En, right, n running from 1 to infinity. Okay, so and we also have that, the norm of U squared is exactly, it looks ugly, not bad, K running from 1 to infinity of the norm of P with the projection of U onto En squared. Okay, now if I write it kind of fully, like this will be summation over K running from 1 to infinity of the absolute value of the scalar product of U. Oops, and let me put EK. This should be EK if I use K. Yeah, I think everything is correct. This will be the summation of the scalar product squared, the absolute value of the scalar product squared, times the norm of En squared, right? But we know that En is an orthonormal basis, so this is 1. So finally, we get that the norm of U squared is exactly summation of the absolute value of U, the absolute value of the scalar product of U and EK squared, K running from 1 to infinity. So with this, we end the proof of the corollary, right? And well, probably, we finished this lecture with a theorem, right, which is kind of very important also to know, and very useful in some situation. So every, this is every separable Hilbert space space has an orthonormal let me drag it. Has an orthonormal basis. So every separable Hilbert space has an orthonormal basis. Okay, so let's go quickly into the proof. So this is the last theorem of this lecture, and also the last theorem of on this on this lecture on the Hilbert spaces, right, in general. So proof. So assume that our Hilbert space is separable. So let Vn, right, be a countable dense subset of our Hilbert space H, right? Now we define Fk, right, to be the span of V1, V2 up to Vk, right? So this sequence is, Vk is a sequence of probably I put it another way, is I would say even non-decreasing. The non-decreasing sequence of finite dimensional spaces, right, such that H is exactly the closure of the union of the Fk. Okay, so now what we do is that to construct our orthonormal basis, so we will pick any unit vector, let's call it E1, right, in F1. Right, this is actually possible because F1 is actually the span of V1, right? So you can probably, and V1 is actually different from 0. Like, you can construct the sequence in such a way that, all the variants are different from 0. So you can actually take E1 to be exactly V1 over the norm of V1, right? So this is exactly a unit vector. So pick any unit vector E1 in F1. Now, if F2 is different from F1, if they are the same, then just keep E1. But if they are different, there is some vector E2 in F2, right? Such that, I feel like it's a bit squeezed. Such that E1 and E2, right, is, so when E1, E2 is an orthonormal, it's an orthonormal basis, right, of F2, right? So repeating the process, you should repeat the process. So repeating the same construction, one obtains an orthonormal basis of H, right? So, and with this we add on. Well, let me just quickly come back somewhere just to explain something. So I said here that if F2 is different from F1, there is some vector E2, but this vector E2 actually follows from, let me put it in color, the existence of that vector comes from the, from the Gram-Schmidt algorithm, right? Gram-Schmidt, I hope the orthograph is correct. So it comes from the Gram-Schmidt algorithm, right? So for instance, probably I use another color. For instance, this E2 will be like, say a U2 over the norm of U2, right? Where U2 is defined to be V2, right? Which is actually an element of F2 minus what? The projection onto F1 of V2, right? This is clearly an element of F2 because remember, the Fk is a non-decreasing sequence. So F1 is contained to F2, right? So similarly, if you want to construct E3, E3 will be like, the norm of U3 over, will be like U3 over the norm of U3, with U3 being equal to V3 minus the projection of V2 onto F2 minus the projection of V1 onto F1. What am I saying? I think I'm getting confused somewhere. But the process of constructing the existence of those vectors E1, E2, E2, E3, and so on actually follows just from the Gram-Schmidt algorithm. Okay, so I think we will stop here. So thank you for joining me, and we see again each other in the next video.